So the next speaker is Cristian Manzoni from the Institute for Photonics and Nanotechnology. And he will speak about hyperspectral imaging and microscopy based on Fourier transform spectroscopy. So the floor is yours.
Thank you very much for the kind introduction, and also thank you for inviting me to give this talk. It was really a pleasure to take part to this workshop where I learned a lot of things, and also I had raised my curiosity on other let's say, fields which are slightly different from this one. So, as the title says, I would like to give you an introduction about what we do on imaging, in particular based on Fourier transform spectroscopy, which is called then hyperspectral imaging. I will give you some examples about these experiments. The experiments were performed at IFN, whose labs are in the physics department of Politecnico di Milano, and indeed the experiments were done in close collaboration also with the people of Politecnico di Milano. Actually, my background is not related to imaging. Imaging came much later. My background is mostly about nonlinear optics and also spectroscopy, so the generation and manipulation of ultra-short light pulses. Here are some, for example, images from our labs, but just to give you an idea. And it was in the framework of these experiments that we came up with an idea of the hyperspectral imaging, a totally unexpected idea, to tell you the truth. So let's see the content of the talk. So first of all, I would like to give a brief introduction about hyperspectral imaging. So spectral imaging means that you collect an image, but from each pixel or each point of the image, you also collect the whole spectrum. And hyperspectral means that actually you collect a continuous spectrum and not let's say, some only discrete frequencies. The whole spectrum you collect. And spectral imaging or hyperspectral imaging can be performed both at microscopic level. So you can study, for example, tissues. You can study spectral alteration of tissues, which means a disease. Indeed, this is very interesting for cancer research, because by looking at the spectrum from your sample, you may understand that something is going wrong there in the chemical processes inside. Or at a, let's say, macroscopic scale, for example, by looking at the spectrum from an object, you can deduce whether something is going, well, let's say, how it is performing. So, for example, it is used to explore the quality of the food by taking simply an image and looking at each pixel of the image. So you can simply by taking one image, you can identify, for example, some degradations in fluid. But this can also be applied for cultural heritage, for example. And at the mesoscopic scale, in principle, you could also take images from space to the Earth. Well, it means that it is really remote sensing, where you can sense what is happening on Earth, so you can control fires and the amount of water and so on by looking at the spectrum of the light coming from the Earth. So these are three possible scales at which you can apply hyperspectral imaging. Now, how is this typically performed? Well, let's say let's see the typical data set. The data set is that at each coordinate X and Y of your picture, you have the spectral information. This is called hypercube. And what you can do with a hypercube, you can either read the information at a specific wavelength, or you can sit at the pixel, you can sit at the pixel. Okay, it's going twice sometimes, yeah. You can sit at the pixel and then you can read the whole spectrum at that pixel. So the hypercube is actually very rich in information. It's a three-dimensional cube, and here comes the problem. The problem comes from the fact that actually detectors are two-dimensional, images are two-dimensional, but you need a third dimension, which is related to the frequency or the optical frequency or the wavelength. So let's explore the typical or the classical way to do hyperspectral imaging. One is let's say, the very intuitive, because simply you take an image, but in front of your optical system, you place filters. So you can select one wavelength at a time. You put a filter, you record an image at a specific wavelength, and then you change the filter, and then you collect many images. Of course, this is time consuming, but also this is limited to the number of filters that you have. In this case, it is six filters, so 6 colors. Another approach, is based on, let's say, it's a sort of a spectroscopic-like approach, which means, well, how to measure the whole spectrum of radiation? Well, by using a spectrometer that here I represent by, for example, this prism here. Well, then, in order to collect the whole spectrum from each point of an image, you can use, for example, a raster scanning approach. This is used in microscopy, for example. You sit at one point, you measure the spectrum there, and then you change the point, and so on and so forth. Another technique, another approach, which is, for some reason, it disappeared here, and probably it really disappeared. I don't know why. Anyhow, so here, no, indeed, it disappeared. The other approach is the one used by satellites, where actually they take a line, an information over a line, and the satellite naturally moves on the surface of the Earth, and so you can collect information line by line, actually on all the surface of the Earth. Another approach, which is basically very different from the previous ones, is based on Fourier transform spectroscopy. Traditionally, this is used in FTIR, for example. So if you're familiar to FTIR, I'm talking about that technique. The technique actually asks you to generate 2 replicas of the light that you would like to measure. Then, with these 2 replicas, you go into the detector, and then you measure the integrated intensity as a function of the delay. And so what you get, if you do this operation, is you measure the interferogram. You get interferogram. And now you do nothing with interferogram. Except that at a certain point, Wiener, Kinchen, and Einstein found out that if you take the Fourier transform of the interferogram, you have for free the spectrum. So you have a spectrometer without a spectrometer. So you have a spectrometer without dispersing light, simply by playing on the delay. And we will see that this degree of freedom of the delay is particularly powerful. We will see later. Now, there are some, let's say, requirements of this. So there are some advantages, first of all. You may have noticed that in order to measure the spectrum, I simply need to go with all the light into one detector. There is no filtering, no spatial filtering, no spectral filtering, nothing. All my light goes into the detector, and all the light goes into one detector. In a normal spectrometer on the Fourier plane, you have thousands of detectors or hundreds of detectors. It depends on the price of the detector. In infrared, they are very expensive. And so that's the reason why FTIR uses this technique to measure the spectra, because one detector is much cheaper than an array of detectors. And also there is another advantage, is that you do not lose energy. And this is the reason why, for example, one of the very first applications was in astronomy, where you have really a little number of photons that you would like to collect. But there is another advantage. And the advantage is that this technique can be parallelized, which means if instead of having one detector, you have an imaging system, so a 2-dimensional detector, and you are able to generate 2 replicas of your light, which in this case, it's 2 replicas of your image. Then what you do is that actually you collect 1 interferogram for each pixel. So if you have 1 million pixels here, in parallel, you are acquiring 1 million interferograms. And then, if you take the Fourier transform from each pixel, then you get for free 1 million spectra. So the advantage of Fourier transform spectroscopy is that it can be parallelized, and so it's very suitable for imaging. And the drawback, of course, there is always a price that you have to pay. The drawback is that you must be able to control the delay between the 2 replicas better than a fraction of the optical cycle. Let's say 1/100th of the optical cycle, which is pretty easy in the infrared, very demanding in the blue, the UV, for example. So typically, let's say the 2 replicas are generated by a Michelson interferometer. Any FTIR, if you open it, it is a Michelson interferometer. Michelson himself had some problems in doing his experiment in 1881. He was more successful in 1887, and the reason is that he took some, let's say, techniques in order to make the interferometer more stable, because the problem is the stability. We by accidental, I would say, some years ago, we built an interferometer, which is actually based on birefringence. This, in the femtosecond community, it is pretty common to use birefringent plates to delay a pulse. Okay, and so for us, it was pretty common or normal to generate the two pulses. So I come from the femtosecond community, and so for me, light was a pulse. For me, light was a laser, okay, only. And it was a laser. Now I'm using also an incoherent radiation, okay? And now and also I learned how easy is to use a laser, because you can easily focus it, you control everything about your laser and so on, and nothing that you can do with incoherent radiation. However, so with a pulse, for example, if you go into a birefringent crystal, you can generate two replicas which are delayed according to the thickness of the plate. Here we decided to use two plates, for example. The combination of them introduces either a positive or a negative delay. This is totally unusable for Fourier transform spectroscopy, because Fourier transform requires that you collect the integrated energy as a function of the delay. However, if you cut one of the two plates into two triangles, and then you move one of the two triangles, actually, virtually you are changing the thickness of the second plate, and so you are able to change the delay. And so this is an interferometer, basically. It's a common path interferometer, so it does not have all the problems of a Michelson. The two replicas are traveling through the same blocks of material, and so it's extremely stable. We verify that it is extremely stable. Believe me, it's of the order of a fraction of the optical cycle, 1/400, not 1/100, but 1/400, even in ultraviolet. And so what we did was, okay, initially we needed interferometer for pulses, and we are still using them for pulses, for two-dimensional spectroscopy. However, we found out that if you shine an incoherent radiation, the interferometer is working anyway. Now I'm pretty used to that, but at the beginning I was very surprised, because I thought that only with a laser you could do interferometry. It's not true. So what we did was to place the interferometer, here it is, in front of a camera, and we said, okay, let's see if we can then acquire a spectrum for each pixel of this camera. And this is what we did, actually. So this is what you see here is the hyperspectral camera, okay, actually. And this is a prototype. This is a camera that we are still using. And there is also a company which is commercializing that. I'm not part of the company, so I have no interest in this. But actually, it's when you develop something that is used for the community, then it makes also our job a little bit more. You feel even more useful for the, let's say, mankind. Well, it's too much maybe, but more useful for society. Now let's see an example. I like colors and so on and so forth. You will see an example which is not typical in this kind of workshops, but let's see if it is working. Yes, it is. Now, let me go back. Yeah, here. This is a glass window. So one of the very first objects that I wanted to take an image of is, of course, was something which was very colorful. I mean, this is a hyperspectral camera to measure spectra, so to measure colors. Let's choose a very colorful situation, and one of the examples is the colored glass windows that you can find in churches. My colleague in my office, while talking to him, suggests, well, there is a church very close to the physics department. Why don't you go there? So we went there. Of course, we asked the permission to the priest there. And so we stayed there. We taken an image of this, which is a beautiful colors. And in particular, then I decided to take some details, and in particular this one. The reason of this is that few months before I took the Camino de Santiago, and so this is the symbols of Santiago. And so when choosing one of the images, I chose this one. We took the image. Now we will show you the result. This is very colorful. So the results already after processing. So I'm skipping all the parts of processing. This is the same image as a function of the wavelength. So you see how rich is the spectral information is this image. At any wavelength, something different happens, from going from the UV to actually the infrared, more or less. This was illuminated by the sun, so there was no artificial illumination. So this is actually what we see by our eyes. And in a sense, I feel limited because our eyes only, let's say, can detect the 3 colors. Nevertheless, we are smart enough to see all the shades of colors, but the spectral information here is incredibly rich. And in particular, then you can do many processing. So, for example, we decided to study how many blue tiles were there in this window, and we found out that there were 5 blue tiles, okay, which were not distinguishable by naked eye, and also we found out that one of the tiles were fake. So at a certain point, probably one broke. They decided to replace that, and it's fake because there is one which is not transmitting in the infrared. It's located one here and one here. 2 of them are fake. So probably something happened. So during a thunderstorm, one of them broke. They replaced that. I don't know if it is plastic or, but anyhow, by naked eye you cannot tell because especially it's sitting in the infrared. This is one example, and then after this, I saw one possibility. Since the very beginning, in our department, there is a group which is working for cultural heritage. So since the very beginning, when I was doing femtosecond spectroscopy, I went to them and said, please, can I do an experiment together with you? I would like to study also cultural heritage, okay? And I always said, no, because with femtoseconds, you can't for 2 reasons. One, you destroy the work of art. Second, typically, we go to museums. It's not the other way around. It's not that the work of art comes to our labs. And so no possibility. Once we had developed the camera, I went to them again and said, look, I have this camera. Is it interesting for you? I said, well, now it is interesting. And indeed, here we'll show another example for cultural heritage. For example, this is a table from, attributed to Michelangelo Buonarroti. Now, this is unfortunately, you cannot see clearly, but I would like simply to show you that, for example, the faces of, for example, the 2 thieves are beautiful. And so it's more likely that it is from Michelangelo Buonarroti. The face of St. John is that, well, let's say terrible. I will not say terrible, but it's not as nice as the other 2. The reason is that, according to this sentence by Vittoria Colonna, it seems that actually there is a secret in this table here. Okay, and she says that she saw the table with a light, with lume, probably a candle light, with a vetro, so probably another kind of glass, probably a blue one, okay, which is opposite to the color of the candle. And she said that non vedi mai più la finita cosa. So she said, well, there is something strange here. What was strange? Well, before I learned about this table before developing the hyperspectral camera, a colleague of mine showed me this table, and she said, by chance, I also have here a blue filter. My colleague had this blue filter. By chance, I also have this blue filter. We can check. And indeed, we saw that the face of St. John changes if you look at with the blue filter. And so I said, well, I'm developing a hyperspectral camera. Once it is ready, this is one of the first things that I would like to measure. And this is indeed what we did at a certain point, once the camera was ready. So now, long story short, this is we took the hyperspectral image. Unfortunately, the light is not helping us, so you have to trust me a little bit. This is St. John reconstructed from the hyperspectral hypercube. This is in the red spectral range, fat fingers, fat face, and so on. And this is in the blue spectral range. Okay, so, sorry. Yeah, here you can a little bit see the differences. Now, we don't know what Michelangelo wanted to do. For sure, he had a total control of the concept of color. Okay, but why do we believe that there is something which is hidden in this table? Because he was part of the Circolo degli Spirituali, which was a secret association in Viterbo, and so, and also Vittoria Colonna was part of that. So now there are some hidden messages into this table, and probably the color itself. Okay, it's hiding some information. We don't know which information is hidden here. But this is the first demonstration that we wanted to see. Then we took many other measurements. We went to the Pinacoteca Ambrosiana to measure Codex Atlanticus, which is really thrilling. I mean, I was doing a couple of experiments on unknown molecules up to a few months before, and then I was measuring the Codex Atlanticus. I mean, it's a different perspective, and it's really beautiful. And then also we went to, this is a score by Beethoven. So we also wanted to measure, I mean, it was not our idea. So we were contacted by the people who are studying Beethoven, and then they asked us to see whether there were some traces of the history of the manuscript. And indeed, we found out that there is a history. Beethoven was not Mozart. Beethoven kept on changing his score by canceling and replacing the notes and so on. Here, for example, you see in green, by taking a hyperspectral image in green, for example, we identified that some parts of the score were done later, okay, with probably another ink. And this is interesting. I come from Bergamo, and the only manuscript in, which is, all the manuscripts by Beethoven are in Bonn, except for one, which is in Bergamo. So it was pretty easy for us to go there, and I was pretty surprised for this. And of course, I don't know if you like music, but actually not to touch because it was forbidden, but to see the manuscript of Beethoven actually is also thrilling. And then also we went to Louvre to do other analysis and so on. So nice, I loved it. I love this kind of analysis. Then we decided to go one step further and to study to apply this technique for microscopy. Okay, so camera easy, microscopy. We then had to couple our interferometer into a commercial microscope. We could do that, and so we could take some different kinds of information. What can you measure from a sample in microscopy? You can measure transmission, reflection, fluorescence, and this was the challenge, Raman. Let's see. So this is the classic. Let's start from Raman, which is the most challenging one. This is a classical way of performing Raman. Yesterday, Dario Poli delivered a beautiful talk about Raman spectroscopy and also SRS and also CARS. This is spontaneous Raman spectroscopy, where you measure the spectrum from each point of your sample. It has some drawbacks, so it requires a lot of time to take the measurements. That's the reason why you select a limited number of points on the surface of your sample, some hundreds of points, or maybe thousands. We said, okay, what about using Fourier transform spectroscopy? Since it is high throughput, because there is no slit, no filter, and nothing, let's use this property to take Raman measurements. You know, Raman light, spontaneous Raman is really very few photons. However, let's try anyway. And then we had also this idea. Let's consider a spectrum like this. You may recognize that it is a typical Raman spectrum plus fluorescence, because always you also collect fluorescence. Now, let's look at that with the Fourier transform perspective. Let's say that what we measure is not a spectrum, but we first measure the interferogram, then we take the Fourier transform and we get the spectrum. So what we measure is the interferogram down there. Now, you may recognize that actually this spectrum here has broadband features and narrowband features. The narrowband ones are Raman. The broadband one is, for example, luminescence or fluorescence. Now, this cannot be uncoupled in an ordinary spectrometer. Of course, you collect both. However, if you collect the interferogram, you can uncouple them. Why? Because actually, at short delays, you get information about broadband information. This is from Fourier transform theory. Broadband means short living. And so this means that around zero, you get information about the broadband content of your spectrum. While at long delays, you only get information about the narrowband content of your spectrum. So we found a way to uncouple fluorescence from Raman, narrowband from broadband, simply by playing on time. This is the advantage of using Fourier transform spectroscopy. Playing on time, you can get some peculiar information. So let's see if it is working. Now, to acquire the Raman, we decided only to measure not the whole interferogram. Well, if we measure the short delay, we get the fluorescence. If we measure the long delays, we get the Raman. This is an example. the microbeads, which are typically used really to measure, to validate a Raman microscope. Typically, also Dario Poli yesterday showed examples with this, and indeed the samples were provided by Renzo Van and Dario Poli. And this is what we measured in color. We colored actually PMMA and polystyrene. And here on the right-hand side, you have the spectrum that we measured in color. So red and green are what we measured, while the gray ones are the corresponding spectra from literature. Now, okay, polystyrene has no problem, but for example, PMMA has a strong fluorescence that we do not collect. So this is not, we have not done any processing to remove the fluorescence. For free, we only have Raman signals, for example. And please note also the following. The acquisition time was 38 minutes for 250,000 pixels. Okay, thanks. Which means that the dwell time is 9 milliseconds, comparable to the dwell time. Dwell time means in a classical Raman measurement, how long should I stay on a single pixel to measure a spectrum? This is the corresponding dwell time. Yesterday, we learned that with a coherent Raman spectroscopy, you can go down to 1 millisecond. Here, actually, by spontaneous Raman scattering, we are at 9 milliseconds, so very close to the stimulated one. But the advantage is the high throughput. Then we also did other measurements. So, for example, we are able to classify microplastics. So here are some examples of microplastics in color. Actually, we colored really the information from the Raman. And you see that the spectra are very broadband, but this is because we decided to take short scans. Okay, but no, don't worry, because, for example, here is another example. This is a real sample from the sea. Okay, from the sea. It was in collaboration with Università Politecnica delle Marche, who gave us the samples. And so this is the black and white. Sorry, this is the black and white image. So no information about that. This is the information with the Raman let's say short scan. And look at the spectra. Now, if I take the long scan, of course, I improve the spectral resolution. But actually, I'm still able to distinguish the two species. In particular, there is a lot of PT inside the sample. And then here is another example where we measure the multi-layer WSE2. And here is an example which shows you the difference between the reflectivity, fluorescence, and Raman. So you can also combine this information in order to learn a little bit more about the sample. Here, for example, we were able to see slight changes in the peak of the Raman, okay, from going from monolayer to bilayer, for example. And also you can see from fluorescence that the monolayer is not uniform at all. So it has some stress inside. Very good. So just to conclude, a perspective. Now, where are we going? Well, different projects. One of them is, for example, to explore other spectral regions, such as, for example, the long-wave infrared or the thermal infrared. The thermal infrared is the fingerprint region, where you have vibrational levels, the same one which are addressed by Raman, but instead of using Raman spectroscopy, you can address them directly by linear absorption, but you need to go in the thermal infrared. You need special detectors, such as, for example, a microbolometer. So with the microbolometer, which is relatively cheap, but thanks to the fact that we use Fourier transform spectroscopy, then you gain a lot in terms of signal-to-noise ratio. This was done in collaboration with the European Space Agency, and this is an image, for example, of a mineral. Now, the idea is from space, can we identify minerals, for example, from their emitted spectra? And how do they emit spectra? Because they are at room temperature. Every body which is at room temperature emits radiation. This radiation has a spectrum. This spectrum is related to the vibrational lines, for example. So this is a mineral. This is what looks like in a thermal camera with no spectral resolution. This is what looks like in a thermal camera with spectral resolution. So we could identify various regions of this mineral here. They are the spectra, and from that we could identify crystal quartz, amorphous quartz, and also, let's say, artificial fused silica. We decided to use these false colors just to identify them. And in order to measure it, of course, we had to heat the crystal. This was a test measurement, but this is sort of light emitted by the crystal. Okay, brings me to the conclusion. So I've shown you the concept of hyperspectral imaging. The way we do that, I showed you some examples for, let's say, remote sensing and also for microscopy. So let me also thank some of the funding agencies for this work, and let me conclude also with the hyperspectral group picture, which is this one. Now, this picture here has this title has two meanings. Hyperspectral group picture means that the picture of the hyperspectral group, but the second meaning is that this is a group picture which is hyperspectral, because indeed this is the visible part of the spectrum, and this is the infrared part of the spectrum. I'm showing you only just two bands, just to give you the difference. And I'm allowed to ask you this question. There is one lady who dyed her hair, and you can clearly see that in the infrared, not in the visible. Okay, can you recognize who colored her hair? Yeah, because in the infrared she's shining a lot different from the other hair. Okay, I was allowed to tell that Daniela Comelli. Now she's not dyeing them anymore, so unfortunately I cannot use it as an example anymore. Okay, that's the reason why this is a pretty old picture. We have a new one, but it was less effective. Okay, with this I would like to thank you for your kind attention.